Harrison for this wonderful talk. Now I would like to introduce our second speaker, another Cambridge alumnus, Dan McKenzie. After being an undergrad in physics, Dan McKenzie did his doctoral studies under Sir Edward Bullard at the University of Cambridge. For his PhD research, he looked for inspiration in the work of Xavier Lapichot. Although Lapichot argued that Hitler observations were not compatible with C4 spreading, McKenzie converted equations to a dimensionless form and illustrated otherwise. Completing his PhD, he went for a tour of United States with a series of postdocs at Caltech, Scripps, Lamont, and Princeton. While at Scripps, he was inspired by the work of his PhD advisor and returned to the problem of using Euler's theorem to describe plate motions. Today, he is going to talk briefly on thermal modular plates on a rigid sphere. Without further delay, please join me in welcoming Dan McKenzie.
This is me, should be, at the time that I did the work which I'm going to talk about. I showed this in I showed this slide in China in January and said, this is me as Harry Potter. The person who was interpreting for me had never heard of Harry Potter. The audience burst out laughing long before he could interpret. The work I'm going to I got involved in all this when I was 24. I didn't actually write my PhD on anything to do with plate tectonics or C4 spreading, but I came to a conference in New York in the autumn and fall of 1966, where all the data from Lamont and from the magnetic anomalies and the Faulkner solutions of earthquakes showed beyond any doubt at all that this was what was going on. So I went back to Cambridge, and while my examiners read my PhD, I did the work which I'm going to talk about in a minute, which didn't take me very long because it was all very obvious how to do things. And that was really a feature of all this. It's, the thing which caused us such trouble is something which is a picture from Harry Hess's original paper, published in 1962. And he said something which Chris Harrison has repeated here, which is completely wrong, and which actually caused us more trouble than anything, which is that he had the material had an upwelling region underneath the spreading ridges. And this upwelling region was a hot sheet of the matter depression. And this then caused us the most enormous trouble in how to think about this. Because here is Teddy's reconstruction, here with the earthquakes down the Atlantic, and instead of doing what Teddy did, here I've simply rotated the two contours either side towards the axis, the spreading axis. the present spreading axis marked by the earthquakes. And you can see that the present geometry of the ridge essentially marks the position of the break between the two continents. And that all looks fine until you look at Africa as a whole. If there's an upwelling sheet underneath this ridge, then what about the one here? How in the world did those sheets know to move at exactly the right speed to stay underneath those spreading ridges? And this was extraordinarily difficult for us to understand. And this really delayed. I remember very much as a graduate student having a conversation with Tuzo Wilson, who was at Cambridge on sabbatical, and neither of us could understand how this could possibly work. And the answer is it doesn't. The solution to this is essentially taken, this picture is taken from the paper that Bob Parker and I published in Nature in 1967, and that has like an interesting history because we wanted to send it off by airmail, but we had forgotten, right, that Little Hoya post office shut on Saturday. So we went down there and we fed the stamp machine with quarters and covered the whole of the front of the envelope with these stamps. One of our friends actually met us there and couldn't understand what we were doing. Alicia Hubbard remembers us doing this vividly. We sent it off to Nature in November. We heard nothing back. We had no referees reports. We had no proofs. And it was then published on the 30th of December 1967. So we just by a hair's breadth made 1967 rather than 1968. And it was therefore the first paper published on plate tectonics. We don't have priority. At that time I didn't know that Jason Morgan had talked actually at a session at the Spring AGU, and it was a session actually in which I was present until he talked. His abstract was all about how the sinking cylinder could explain trenches. And I didn't believe a word of this. He'd been interpreted to the Mont data, so I left before his talk. Because Jason, typical of Jason, he didn't talk about that at all. He talked about plate tectonics. Nobody understood except Saki Lepichon what he said. This picture is taken from figure 3 of a paper. And at that time, I had not had nothing to do with essentially presenting observations. And this is a rotten picture. It shows the slip vectors of earthquakes around here, but it shows no data at all. What we should have published is this. Here's the actual slip vectors in the oblique locator projection that we used. These are actually the ones that we used. And to determine the polar rotation of the two plates, what we did was to take a National Geographic globe, mark on those with a marker pen, the slip vectors, and then fiddle with the cap until we could get a decent fit to these slip vectors, which is one way of doing it. We got the pole very close to what it is now. This is an illustration. You don't need fancy mathematics to do simple things. This was the thing with it. I have two regrets. One about that paper. One is that our presentation of the data was so bad. The other one, which is much more complicated question, which is that what we didn't do, but we knew and noticed, was say anything about the Hawaiian Ridge. This is the Hawaiian Ridge in that same projection. And quite clearly, Hawaii is in some way knows about the fact that the Pacific is moving. And we didn't say anything about it because what we wanted to do was to construct the whole theory in terms of relative motion rather than absolute motion. Right? So we didn't mention this, but we were perfectly well aware of it, but we had no understanding of it at that time. Now, what the other paper I published in almost the same time, 1967, was one which Chris Harrison talked about, which is essentially the spreading on ridges as could account for both the heat flow and the elevation. And the idea is really very simple, right, which is that the ridges are completely passive features. Underneath, the isotherms are horizontal, and the whole thermal structure of the ridges results from the upwelling generated by the separating of plates. And clearly, this then completely avoids the problem which we had with Harry Hess's scheme, because ridges have no deep structure. This paper actually this picture was published by my head of department, Lord Oxborough, in 1980, and he should have known better, but he was a student of Harry Hess's, so he put, even as late as 1980, the plume underneath the ridge. Really, it's impossible to do that. But if this is correct, all kinds of things then follow from it. You have to be able to account for all the features of the ridge by passive upwelling between separating plates. And my first attempt to do that, which was published also in 1967, shown here, and this is also almost entirely wrong. But rather like Harry Hess's picture, then the idea was not wrong. But what was wrong here was that I was trying to explain everything, right? Both the depths of earthquakes, the rigidity of plates and everything, by choosing a certain thickness of plate. So I chose 50 kilometers, and that was designed to essentially match the 50% line here of the heat flow plot. The plate is too thin, and the temperature beneath the ridge axis is too low. But the idea of using essentially fluid dynamical ideas, of making everything dimensionless, and using a simple analytical model was not wrong. And what then happened was that John Slater, who I'd say is here, right, with Barry Parsons, then took this, essentially this really simple model, and showed that it was consistent both with the heat flow and with the substance. And this really, this paper had a very profound effect on me, because it showed really for the first time how you could use really simple physical ideas and analytical models to account for geological observations. Here's their fit. What I'll draw your attention to is this gap here. They only used dates, the seafloor, which they could date with magnetic models. And this is very important. So this is the period in the late glaciers when there weren't any reversals. So there's a gap there. This is the model they came up with, which is essentially correct. What we can now do is something rather more sophisticated. This model, this is the same thermal model as I was just showing you, but now taking into account the fact that the thermal conductivity is a function of temperature. You can see the spacing here between isotherms here is about twice that down here, because the thermal conductivity decreases with increasing temperature. The earthquakes here in the oceans, controlled by waveform modeling, all are in regions which are colder than 600 degrees centigrade, which is true right up to the ridge axis. The subsidence here now fits. This is the points here are from Alistair Crosby. And notice here that there is a deflection up here. That, I'll show you in a minute, we believe now is due to the fact that actually as the plate cools, the bottom goes convectively unstable. The heat flow now, and this is log of the heat flow because variation is so large, that also now fits very well. But unlike what Barry and John did, almost everything here except the thickness of the plate is now controlled by laboratory experiments. So we have no freedom, which they used, to fit the data. In fact, the laboratory observations agree excellently with the fits that they got. So everything's fine. So this looks like their thing, but isn't actually, because it's controlled, as I said, by laboratory experiments. And this bump, right, so this is the bump, I think, is real, but the scatter in the depth observations is really rather large. You can see these are two. This is Alistair's, right, this is Mark Hogarth's. You can see that the scatter is really quite large, so it's somewhat, I mean, seeing it from the depth point of view, it's not that convincing. Now, the new thing which we can now do is use surface wave tomography to look at the velocity structure of the upper mantle beneath, in this case, the Pacific. And here is the age distribution, and here is the velocity at 150 kilometers. Now, this is below the bottom, the best fitting plate thickness now for the Pacific is about 100 kilometers. So you can see here, there's clearly a change in the velocity at this depth from here beneath the ridge going up towards the northwest. And various people have claimed that this actually means that a plate model for the cooling isn't correct, that actually you need a half-space cooling. Now, I'll show you in a minute that argument is not correct, but the observation here, that the upper mantle is cooling is indeed correct, and that must be the case, if you think about it, because I go back to the heat flow, that part of the Pacific, or part of the Pacific is losing heat, so it's cooling. The amount of heat being generated by radioactivity in the mantle is essentially negligible. If you take a block of mantle and put it in an insulating box, its temperature increases by 7 degrees per gigayear, which is completely negligible. So this cooling here, this heat flow, the heat flow through the surface, must actually be associated with the loss of, with the cooling of the mantle somewhere. What the depth observations show is that the material that's cooled is not rigidly attached to the plate on top, but detaches. We can now see that from the surface wave tomography. What we did, and this is with Keith Priestley, here's a stat velocity from the surface wave tomography showing as a function of age. You can see here clearly the cooling of the plate that goes and the isotopes being horizontal below. But what you've got to do then, if you want to do this, the velocity, we know from arguments which I haven't time to go through, that the velocity is controlled by temperature and not by composition. That in some sense is obvious from this picture, because I'm using my, get this one to work for this one. Don't have a stick, I've always found these. Can I borrow yours now? Looks as if it extends too. Remember, the velocity is controlled by temperature, but it's a very complicated business because it's actually not the solid material, it's the grain boundaries which control the velocity. They become weak as the temperature goes up, and that is what's causing this. So somehow we've got to convert from velocity to temperature. If you try and do that using laboratory experiments, you get into trouble because the the grain size you can use in the laboratory is limited to no bigger than 25 microns. The grain size of the mantle is about 1 millimeter. So how do you do it? Various people have tried to extrapolate over several orders of magnitude in grain size with no decent tip. What we chose to do instead was to take the geological and geophysical observations, take our plate model, use that then. The plate model, we know the temperature is a function of depth, we know the velocity is a function of depth and age, so we can then plot the velocity here as a function of temperature at different depths, 50 kilometers and 75. And that's what's shown here. And you can see the effect. There's a really sharp change in the velocity with temperature at high temperatures. And this is really very striking, and it's also seen in the laboratory, but it's this which is really we're going to use to look at the temperature beneath the temperature of the plates. And this, we then got to parameterize it, and this is a picture essentially showing how well we do with the parameterization. This is a comparison. I explained the dot points there are nodules, right, from kimberlites. The curves are from specific velocity structure. This is the misfit here between our parameterization and the observations of the velocity at 50 kilometers. This one's at 70, and this is the misfit for the nodules. We think our measurements of the velocity are good to about, probably a bit better than 0.1 kilometers a second. So you can see that the spread of all these is really comparable to the errors of our measurements. So we could then turn our velocities, that velocity picture, into temperatures. And this is a comparison showing the velocities of those blue dots, and I just simply used a cubic spine interpolation to produce a continuous curve. The red lines are from the plate model. And you can see then, as we get colder, here at 5, 25, 65 million years, the plate model does a good job, but from 65, 75, and 115 million years, the observations from the surface waves, actually the temperatures there are hotter than those of the plate model. And this, we think, is the result of the bottom boundary layer, the bottom of the plate, going convectively unstable. And by 135 million years, we're back to fitting. So you can then take the velocity models from the surface wave tomography and compare them with actually what we see in terms of depth age. And this shows this comparison. Here's the one, depth age from Alistair Crosby's data. This is the calculated one from the surface wave tomography. And you can see, and this is from Mark Hoffman, and you can see that there is a deviation. It's hard to tell whether actually it doesn't come in exactly the same place either as Alistair's or as Mark's. But it's clear that something is going on here, some instability, and that's actually what is causing the bottom of the plates to stay warm, and why we can use a plate model for looking at all this. The other thing I tried was to see whether actually you could see the deeper temperature structure of the mantle getting colder as you go across the Pacific. And this is an oblique Mercator projection of the surface wave tomography velocities, also at 150 kilometers. And what I then did, if it's going to be an instability, what you actually should see is that as you go this way, you would expect that the velocity of the mantle would slightly increase as it gets colder. Well, you can't quite see that. Here is the view of the velocity, the temperatures from the
the surface wave tomography. And this is then an isentropic curve from the mantle. And I can't really see any convincing evidence that there's any difference as a function of where you are. So I can't see that the deeper structure of the mantle actually gets any colour. I can't see it. I'm pretty much. So we're not quite there with seeing what happens to this cold material that drops off, but Keith has just produced a new surface wave tomography model using 5 million seismograms, 20 terabytes of data. And I haven't yet had to do that 2 weeks before we came here. I haven't yet had time to look at that. But it's quite astonishing to me that we can now actually get the temperature structure from surface wave tomography. And that it agrees so well with what originally John and Barry did, and then with what we did, and with the laboratory observations. So, in conclusion, I think plate tectonics is alive and well after 50 years. It's required really very few changes since Bob and I first published that paper. And I don't expect that to change. It's now, the thing that might have changed it was GPS, and all GPS did was to find a small error in the decay constant of potassium 40. The third structure of continental the spheres together form a boundary layer, I think is very well done. I think our understanding of geodynamics is incomparably better than it was when I became a graduate student. I will be surprised if anybody in the future has the sort of opportunities to do major changes like I did when I was 24 and 25, and Fred Vine did in his first year as a graduate student. I think the resistance to basically what should have been obvious, which was that the fit to the South Atlantic continents really required explanation, and that's been known for a very long time. That sort of resistance is now no longer a feature of the Earth's sciences, thank goodness. But it does mean to say that starting graduate students don't have nearly the same opportunity to overturn decades of prejudice.